Hello and hi everyone. My name is Samir Shad bin Saiful under supervision of Dr. Kamya Shamili, and I'm going to present about cross-linked chitosan-based hydrogels nanocomposites for the treatment of viral disease. There will be four main points in the introduction, which are hydrogels, biopolymer and cross-linker, chitosan and antiviral. For the hydrogels, hydrogel characterized as a polymeric structure where the chains are connected by non-covalent and to form a three-dimensional network. Hydrogels are formed primarily by electrostatic interaction with the hydroxyl groups located at carbon 3 and carbon 6 and the amine group located in the position of carbon 2 of the 1 unit. Therefore, it appears to form cross-linked three-dimensional structures with dialdehydes which are used, for example, to grow proton conductivity membranes that may be used in fuel cells. Biopolymer are polymer of biomolecules that contain one units that are covalently bonded to become bigger molecules. Material derived by synthetic chemistry from surroundings such as vegetable oil, sugar, fats, and etc. can identified as biopolymer. Cross-linking is well known as the typical method to overcome the biomaterials limitation. Cross-linkers bind molecules, enhance molecular weight, and give better mechanical properties and stability in general. However, cross-linking reduces degradability, decrease disease the availability of functional groups in the cross-linked polymer. Chitosan is made from chitin, which through process partial deacetylate. To form chitosan nanoparticles, there are three ways of chitosan cross-linking method, which are chemical cross-linking, radiation cross-linking, and physical cross-linking. For chemical cross-linking method, chemical cross-linkers are glutaraldehyde, genipine, glycol, dextran sulfate, 1,1,3,3-tetramethoxypropane, among others. Next, radiation cross-linking method does not need heat or catalyst, which means no additional toxin is involved. In contrast to chemical cross-linking, which is achieved through covalent bonding, physical cross-linking is achieved by the use of cross-linker that establish ionic contact between the polymer chains. Antiviral and antibacterial polymers come in a variety of forms, ranging from natural biopolymers with inherent antiviral or virucidal capabilities to manufacture thermoplastic elastomer. Antiviral properties is also depends on biopolymers properties. As example, sulfonic functional groups in antimicrobial polymers and polysaccharides like glutamine and fructosan perform well against virus adherence. Hydrogels are frequently regarded as biocompatible and they can be utilized to contain antiviral inorganic elements or synthetic polymers. In 1811, chitin is considered as the second highest of polysaccharides on the earth, being first described by Henry Braconat. Its natural abundance that make it possible to obtain more than 1,000 tons per year and marine organisms are the major sources which is about 70%. Table below shows chitin and chitosan resources. They are from microorganisms, sea animals, and insects. As you can see on this slide, there are two molecular structures. On the left hand side is chitin and on the right hand side is chitosan. Chemical structure of chitin made up of 1,4-link 2-acetamido 2-deoxy beta-D-glucopyranose. The most typical type of chitin is alpha chitin. Its unit cell made up of N,N-diacetyl chitobiose units arranged in two antiparallel strands. As a result, adjacent polymer chains are kept together by 6HO6 hydrogen bonds, while the chains are maintained in sheets by 7Hn hydrogen bonds. For the chitosan is distinguished from chitin by the presence of amino groups, which is reflected in its solubility in dilute acid, pH 6, as well as its ability to form complex with metal ions, allowing it to be used for wastewater treatment and purification. Chitin, on the other hand, has a very few practical applications due to its low solubility, if any. Chitosan, a linear and semi-crystal polymer with at least 60% of its glucosamine residue deacetylate, which corresponds to a deacetylation degree of 60. Chitin deacetylation is accomplished either chemical hydrolysis under harsh alkaline condition or enzymatic hydrolysis in the presence of certain enzymes such as chitin deacetylase. On the next slide is chitosan-based hydrogel. Cross-linking of chitosan polymers is necessary to improve chitosan properties such as stability and durability for the aim of drug delivery. Chitosan-based hydrogel networks are categorized based on the method of chitosan cross-linking and preparation. Therefore, there are two methods of chitosan-based hydrogel preparation, which are via chemical cross-linking method and physically cross-linking method. For chemically cross-linked aerogel are formed by covalent linking of the chitosan micromers, where the bond formation is reversible. Which is irreversible. Chemical cross-linked hydrogels are found in four states of formation, which is shown in below, the diagram below. The A, chitosan cross-linked system. B, hybrid polymer networks, HPN. C, interpenetrating polymer networks, IPN. And D, semi-interpenetrating polymer networks, SIPN. The simplest type of chemical hydrogel formation occurs when chitosan undergoes cross-linking reaction with another polymeric chain of its own. Second chain can be similar to or different from first structural unit in derivation. Amines and hydroxyl groups is situated on chitosan chains are responsible for chemical cross-linking. Chemical cross-linking can occur via cross-linkers or photopolymerization reaction. For physical cross-linking method, physical cross-linking to form chitosan-based hydrogel networks is another class of cross-linking. Physical interactions can be ionic interaction, as in ionically cross-linked chitosan hydrogels and polyelectrolyte complex, can be secondary interactions such as networks named crafted chitosan hydrogels and entangled chitosan hydrogels. For the first one, which is ionically cross-linked chitosan-based hydrogel, since chitosan is a cationic polyelectrolyte polymer with ionizable amine groups, and ions are often employed as ionic cross-linkers to engineer ionically cross-linked chitosan hydrogels, shown in the right-hand side of the slide. One of the examples is the multivalent counter-ions such as phosphate-pairing molecules like tripolyphosphates, TPP. This ionic cross-linking process, which is called ionic gelation of chitosan, is mostly used for loading of low molecular weight drugs, but recently has been used for macromolecules as well. Polyelectrolyte complex networks are formed via ionic interactions between two opposite charged polymers. Polysaccharides are good choice for preparing polyelectrolyte complex because of biocompatibility and biodegradability. Oppositely charged, polysaccharides interact with each other in the solution spontaneously and form polyelectrolyte complex. Chitosan is positively charged, thereby, a negatively charged natural polymer like alginate, pectin, carrageenan, xanthan gum are suitable candidates for such interaction. Formation of this polyelectrolyte complex depends on a number of variables including the charge density of the polymers, mixing ratio, amount of each polymer, etc. Solubility of the resulting complex also depends on the net charge. If the net charge is zero, then the complex will usually be insoluble and precipitates. Last part is biomedical and antiviral application. Chitosan has found attention in many different fields including pharmaceutical, medical, cosmetics, agricultural, and food industry. The pharmaceutical applications of chitosan include drug delivery, wound dressing, and tissue engineering. Hydrogels based on chitosan and its chemical modified forms are investigated in several drug delivery applications. Chitosan has cationic nature due to the presence of amine group and mucosal glycoproteins are negatively charged. Therefore, it can adhere to negatively charged biological surfaces as a bioadhesive material. The use of bioadhesive polymers like chitosan prolongs the residence time of drug-loaded system and provide localized drug delivery. Chitosan also mediates paracellular transportation of drugs that greatly influence efficiency of drug delivery system. As chitosan is a biocompatible and biodegradable with a structure which could be modified easily, it has been used as drug carrier for different routes of administration. Next, Chitosan in topical form is used for wound healing. The probable mechanism of healing is infiltration of inflammatory cells such as polymorphonuclear leukocyte, secretion of inflammatory mediators like tumor necrosis, factor alpha, migration of macrophages, and increase in the amount of collagen. The major use of chitosan hydrogels for wound healing is using these systems as wound dressing and hemostatic agent to promote the process of wound healing. Last but not least is tissue engineering. Chitosan hydrogels were used as scaffolds for tissue engineering in the past 2 decades. The foundation of this system relies on two components, cells and polymeric chains of hydrogel. Biodegradability is amongst advantages of chitosan as a scaffold. Chitosan can be degraded with human enzymes like lysozyme. Chitosan scaffolds can be used for regeneration of various tissues such as bone, cartilage, skin, and nerves. The treatment of central nervous system disorder (CNS) is challengeable because neural cells have lower ability for regeneration. Nerve tissue engineering requires neural stem cells such as embryonic, fetal, or adult stem cells. That's all from me. Thank you.